and today I will be talking about my project I have been working on lately, which is accelerating SuriCata by filtering network traffic in hardware via DPDK framework. So, more about the background I'm coming from. I work for a company called CESNET. We take part in administration and development for National Academic Network, and I'm part of a department called LibreRouter, where we develop and administrate security tools. This work is also a part of a thesis I'm working on at Faculty of Informatics at Masaryk University in Brno, Czech Republic. And the project is supervised by a person you may well know, who is a SuriCata team member, Lukas Šishmiš. Now, let's look at the agenda I will be discussing today. Some background and motivation on why we decided to implement the features we did. Then more about RT flow rules in general, which is the backbone technology this acceleration of SuriCata is performed by. And then the first implementation, or the first feature we have implemented, which is the static drop filter. We call it the static drop filter. And then the second feature, which is dynamic bypass, also performed via the RTE flow rules. In the end, I will present you the results we have achieved and some more about the future work we will look into. So more about the motivation. Background. So we know we are all on the same page. DPDK is a high-performance capture method that's already present in SuriCata. And it's also a library collection containing optimized memory data structures and memory handling. RTE flow is a subset of DPDK, and it's a generic way to configure traffic rules in hardware. It performs an extensive network traffic pattern matching capabilities. From now on, when I will mention pattern matching capabilities, I will be talking just in the terms of RTE flow rules, meaning that the pattern are consisting of different network headers. And another another positive side of using RTE flow that it offers a vendor agnostic approach, as we are at CESNET working with multiple different network cards, namely the MLX5, I40, ICE, and IXGBE cards. We want also in SuriCata and for easier handling of these cards to have one unified interface which DPDK and mainly the RTE flow API offers. So why we decided to accelerate SuriCata? Well, there are multiple ways or multiple types of flows we don't need to see in SuriCata. For example, with TLS, we just need to see the handshake. For large flows, it's often enough to see just the first n bytes of the flow, and we can sometimes completely ignore traffic from known sources. This optimization can save us resources such as memory, CPU cycles, or NIC descriptors, which can lead to inspecting more of the potentially malicious traffic. Now, what are the RTE flow rules? RTE flow rules are generic rules offloaded to NIC via DPDK API. As you can see on the diagram, we have some DPDK application, in our case, SuriCata. And there is the main function for creating RTE flow rules, which is called RTE flow create. The application creates the rules and loads them into the hardware with this API call. And from now on, the rule lives in the hardware until changed otherwise. Either the application can destroy the rule, or it's automatically or should be automatically destroyed when the application ends. That's assured by DPDK. The main plus side of using the RTE flow rules is that blocks or it performs directly in the hardware, meaning that we can save the CPU cycles that would be performed otherwise in the application in SuriCata, or also we are saving the PCI bandwidth that would the NIC use to transfer the packets into the application. What does a RT flow rule look like? It consists of three main parts. Those are attributes, which describe the general behavior of the rule. We can describe whether it's ingress or egress, or we are matching the incoming or outgoing traffic on the interface. Then we can specify the priority or group attributes. So then, this way, we can create a sort of a hierarchy of rules in the hardware. The matching pattern part consists of the pattern we want to match for the specific rule. We are specifying the network protocols and their specification. For example, we can use some Ethernet MAC address or IPv4 source and destination address, TCP ports, etc. And with the action part, then we are describing what is going to happen to the matched packets or the matched traffic. We have a lot of different actions available. Mostly it depends on the NIC used, but some of the general ones are RSS or receive side scaling, configuration, drop for dropping the traffic, count, mark, and so on. Now we'll look closely more at the drop filter, which is the static filter with the predefined traffic rules. It is kind of a BPF-like filter built directly on RT flow rules. It uses predefined traffic patterns that are configured before the start of Suricata in the suricata.yaml configuration file. And its goal is, as it seems, to reduce the load that is passed on Suricata. As we can see on the diagram, it's quite straightforward. We have multiple flows coming into Suricata. We described with the pattern that the flows we want to drop, and just the other flows are passed into Suricata, meaning that Suricata doesn't see the flow completely. It's completely blocked in the NIC or dropped. We can drop this way some verified or safe traffic, traffic with forbidden inspection. For example, if we have a company or some higher policy that we cannot inspect some flows with our Suricata, we can assure this way that the flows are not seen because there isn't a chance for Suricata to even see them. Other flows or other traffic that can be dropped is, for example, some YouTube, Netflix, streaming services, data backups, etc. It's important to note that a drop filter is built purely on IP addresses, TCP ports, and network header specifications, meaning that we cannot specify the host names. It's purely on the network. It's purely built on network headers. As for the current state of this feature, we inherited the syntax from DPDK test PMD application. A DPDK test PMD is an DPDK application for testing RT flow rules. It's command line application, so it's quite easy to use, and we can see the pattern defined here. We inherited only the pattern part, otherwise we would need to specify also the action and the attributes. And for example, how would a pattern in Suricata be described is here. We define the pattern keyword to let know the parser that we are parsing the pattern. Then we define the headers we want to match in the order you can see. And in this order, it's supposed to be present when it's matched in the NIC. We have the Ethernet header, then some IPv4 with specification of this specific source address and this specific destination address, and then we ended with the end keyword. For example, there could be a rule that also matches some specific TCP port, or we could have a rule that matches a range of IP addresses, or we could have a rule that that matches based on a mask of IP addresses. When we are developing this feature, we are discussing what syntax to use. There was an idea to use a BPF-like or BPF syntax, but as RT flow rules don't support all of the BPF features. For example, RT flow rules don't support negation of the defined pattern or operation inside of one rule. We decided to not use the BPF syntax. There is a current ongoing effort to extract the parser of the RT flow rules outside from Suricata and integrate it directly as an API to DPDK. This is work currently performed by Lucas, because in the current state the parser is in Suricata. And also there was a discussion to exclude the feature completely from Suricata into a plugin, and this was discussed in a pull request and is being thought about and literally worked on. As I said before, here's a visual representation of how the rule in Suricata looks like. We have the attributes and actions which are defined by Suricata, and they are automated. So the Suricata operator or the Suricata user can specify only the pattern part. Here we can see how are the rules configured inside the Suricata YAML. Under the DPDK section, we can see the interface list, and under the specific interface, we have the drop filter section where we specify the patterns we want to drop in the NIC one by one. For example, here we have multiple rules that drop specific IP addresses, either source and destination, or some source with this mask defined. We also wanted to measure the traffic that is passed into Suricata and dropped, or that is dropped in the NIC and is not passed to Suricata. Somehow, we are utilizing the hardware counters present on the NIC, and RTFlow offers count action to retrieve these counters. This is supported only on the MLX5 and ICE cards that we are working with. As I40 doesn't support the counters or the count action, that we cannot retrieve them, but we are still supporting the feature. The counters and the statistics from them can be used for verifying whether the filter is active. We can measure the performance of the filter and the Suricata as a whole, or we can evaluate the statistics in the global scope. Now let's look at how the Suricata lifetime from the aspect of creating and querying the drop filter rules look like. We have a Suricata starts, then we perform the RT flow create one by one, or API call one by one for each rule. In the receive loop, there is a periodic counters check where we, for every rule, call the RT flow query API call, and this throughout this we return we gather the statistics, namely the bytes and the packets that were hit by the rule. With these statistics, then we can update the global stats and continue the runtime. As for the testing, we had a lab setup as follows. We had a Trex traffic generator for generating the traffic. We had a switch which had one mirror port. As you can see on the diagram, the switch mirrors one specific port, which sends also ingress and egress traffic into Suricata, so we can see both the client and server side of the traffic. And as for the Suricata machine, we are using a 20-core CPU, 10 on one NUMA node, 10 on second NUMA node, which not all of the CPU cores were utilized. We have been using 64 gigabytes of memory. 6 of those were huge pages and 100 gigabit network interface card. As for the configuration of Suricata, we were using 7 CPU cores as workers for analyzing and capturing the packets. Then we were using 3 CPU cores for managers, such as the flow manager or the flow recycler, and we were testing with the emerging threads open rule set. As for traffic profile for this specific test, we chose 99% of the HTTPS traffic on the port 443 to be filtered, and just 1% of HTTP traffic to be supposed to pass to Suricata. This test was mainly performed to showcase that the filter is active and the filter is performing as it is supposed to. So I will show you in the next slide. And we are testing on a 200-second duration of traffic generation. So now we can take a look at this graph. On the y-axis, we have a throughput achieved in gigabits per second. And on the x-axis, we have a category of the packet drop rate. Now we are measuring at just 0 loss. With the filter on, we achieved basically almost the maximum of what the NIC can achieve, which was 90 plus gigabits per second, meaning that all of the traffic that was supposed to be dropped was dropped without any performance issues. And on the red part of the graph, we can see the category where the filter was off, it was inactive, and we achieved just around under 15 gigabits per second of throughput, meaning that it just straightforward showcases that the filter is working as it's supposed to. Now, for the dynamic bypass, we are implementing the RTE flow rules for. As many of you know, the Suricata signatures can specify the bypass keyword for bypassing any of the flows that are described there. Here we have an example where we are bypassing the HTTP traffic going to Suricata IO. This means that the rule for the bypass is created at runtime, meaning it's not predefined. Also, Suricata offers different ways to bypass flows, such as we can, in the Suricata.yaml, configure bypass of all encrypted flows or of flows or part of the flows that are above some reassembly depth or that had reached some reassembly depth. We also performed a test that I will show you later on this type of bypass. So as for current state, there is some bypass, but also when DPDK has these hardware capabilities, it's only in software, as with some other capture modes. And our goal again with this was to reduce the load on Suricata by utilizing the RTE flow with full potential. With this feature, it was also important to keep in mind we needed to delete the rules, as the NICs have limited capacity. Sometimes it's not even, the capacity is not that high with the NICs that we are working with, so we needed to maintain it at a certain level. And the initial idea for the bypass was to create the rules, drop packets. If the NIC timeouts the flows, meaning that there is a way to configure the NIC to send an alert or event to the application when the rule is not hit for a certain amount of time, and based on this event, we would destroy the rules. This used a combination of two actions, which is drop action for dropping the traffic and age action for issuing the events after the period of time on seconds. The disadvantage of this approach was that we were limited only to the MLX5 NIC, as the age action is not supported on other NICs we are working with. This was not general enough, as we want to support more types of NICs. So we decided not to use this approach, and what we decided to use is approach as follows. We are creating the rules, dropping the packets, and then the Suricata performs the periodic check, not the application, not the NIC, and also Suricata manages the timeout. We are doing it with drop and count RTE flow actions, meaning that we are retrieving the hardware counters of the rules that are present in the NIC, and based on the statistics we gather from the rules, we decide to destroy them as we deem them not active, or we decide to keep them as we see they are still filtering the traffic. We don't want to since Suricata we are bypassing. This action this approach is supported by both MLX5 and ICE cards we are working with. And as the I40 card type of cards don't have the count action available, or we cannot retrieve the counters, we cannot check for the activity of the rules, meaning that we cannot destroy the rules. So we are not supporting this type of card. Also, this approach utilizes a special thread called bypass manager for loading the rules into the network interface card. Now, just to give you a background, how does the Suricata trading model look like from our perspective? We have the workers that poll the NIC and analyze the packets. Also, they are sending the necessary information to bypass manager for creating the flow rules or the bypass flow rules via a ring structure. We are utilizing this because the RT flow create that the bypass manager performs, which creates the rules, is not asynchronous, meaning that the application needs to wait for the thread needs to wait for the API call to return, which we are waiting for the rule to be loaded. As this would slow down the workers, we decided to make this process more asynchronous by sending the necessary information into the bypass manager via the ring, and the memory are pre-allocated. And then we have the flow manager, which manages the flow table, and in our case also queries the counters of the NIC and of the specific rules, and possibly destroys the rules if they are inactive. Now we'll look how does the process of creating the rule look like in Suricata. As the worker thread gets the packets and deems the packet as to be bypassed, the flow is added to the flow table, and we pass the flow attributes to bypass manager as I described. We are using the RT mempool structure for allocating the memory, and the RT ring a structure to pass the necessary information into the bypass manager thread. Then the bypass manager creates the rules via the RT flow create. The bypass manager thread is responsible only for creating of the rules, so it doesn't matter if it waits or not. It doesn't affect the performance of Suricata. If the rule is created successfully, we set the state of the flow as capture bypassed. From now on, the statistics of this rule will be visible under the capture bypassed stats, for example, in stats.log. And we add it to an internal structure called flow handler table, which manages the association between the opaque handlers of the rules present in the NIC and the flows present in, or the flow structures present in Suricata. In the other case, that the rule is not successfully created, that could happen when the capacity of the NIC is already used up, or in other unspecified event. We set the flow into the state local bypassed, and now we let Suricata handle the bypass in software. As for querying and destroying the rules, querying the counters, there is a periodic check of the counters or of the bypassed flows in the flow manager, and it looks as described here. We, for every bypassed flow, query the hardware counters in the NIC, and the NIC returns us the bytes and the packets that were hit by the rule. In the case that the filtered packet count or the hardware counters were 0, we destroy this rule and remove it from the flow table. Meaning in this process that we basically don't waste the capacity of the NIC. As for the testing, we performed with the dynamic bypass to showcase that with the use cases where it's the most applicable. For Suricata configuration, we used 7 worker CPU cores again. Again, 3 CPU cores for managers. One of them right now is also the bypass manager. And we are bypassing all the flows that were longer than 500 kilobytes. And again, we were using emerging threads open rule set. We are using the same topology as described before with the drop filter testing. As for the traffic profile, we are using 27 megabyte long or large elephant flows that were supposed to activate the bypass and above the 500 kilobytes be bypassed in the hardware, and smaller 41 to 42 kilobyte flows, HTTP flows that were supposed to be actively analyzed by SuriCata. Again, we were testing with 200-second duration. As for, we are always performing 4 tests and averaging the drop rate. Again, on the y-axis, we can see the throughput in gigabits per second. On the x-axis, we can see 2 drop rate categories. We are measuring at 0 loss, and we are also measuring at 1%, up to 1% loss. On the left side, we can see that the drop rate is quite similar in both use cases, as this can be attributed to also the type of testing we performed, as most of the drop rate is present at the start of the traffic generation, meaning we had to lower the speed to get to 0 loss, and at this speed the bypass is both RT flow bypass and the bypass on the main branch is similar. But on the right side, we can see that when we allow some drop rate to be present, we could achieve almost 40% higher results, higher throughput with our RT flow bypass. Also, I didn't mention that this is testing in an environment where there is 3-to-1 ratio of elephant flows to short flows. This showcases in general that the bypass is mostly applicable in environments with a lot of large flows that can be bypassed. In the other test we performed, we are testing on an environment with 1-to-1 ratio of elephant flows to the short flows, as described 2 slides before. Again, we have a similar layout of the graph. On the left side, at the 0 loss, and both on the right side at the up to 1% loss, we were achieving quite similar results, meaning that, and proving my point that both the versions here at environment with a similar ratio of the large flows and short flows, the filter or the bypass is the both types of bypass are similar performing. That was about the testing we have performed. And now a little bit more about the constraints we are facing with using this approach. As the cards, as I mentioned, have a limit, or all of the cards have a limited number of rules they support. Mainly the MLX5 we have used for testing and are mainly developing this feature on, has support of around 65,000 rules. We cannot use or it's not viable to use top 10% of this capacity, as we have during the development of this feature run into these 2 papers from Brno University of Technology and KTH Royal Institute of Technology, that the top 10% of this capacity of these cards has higher drop rate, or lower throughput, meaning that the drop rate at the same speeds is lower, and also the insertion rate of the rules in that capacity is much higher. Then we need to limit the maximum, or hard cap the maximum number of rules that is viable to use. And also with the capacity, as RT flow doesn't support bidirectional rules, meaning we need to create 2 rules per 1 flow. So we are practically halving the capacity by 2, or halving it. And With ICE driver that we are, or the cards with ICE driver that we are supporting, they support only 256 rules, meaning around 128 flows can be bypassed. And we didn't yet test the performance on this card, but we are planning to. And in the end, I would conclude my work and mention what we are going to do in the future. So, just in short, RT flow rules, they are rules present in the NIC that can perform various operations on the present network traffic. We can drop it, modify the traffic, etc. The drop filter is statically pre-configured before the traffic or before the Suricata is launched, and it just drops the defined traffic. With the dynamic bypass, the rules are created at runtime, meaning there is some overhead of creating it. And with the testing, we have achieved in the environment with the more elephant flows than the other flows, shorter flows. We have achieved around 40% throughput increase, and around we bumped the performance per core from 1 to 1 gigabits per second to around 1.6 gigabits per second. And for the future work, there is also a different type of RT flow API for creating the rules. It's called template API. It basically is asynchronous. It supports asynchronous handling of RT flow rules, meaning we don't have to wait for the operation to finish, and we can continue our operation of destroying or creating the rules. We don't have to wait for them. We can just we can continue with the thread performing further. Also, this API allows us to pre-allocate resources for the rules in the NIC before the specific rules are created, also saving us some latency while creating the rules. Currently, with the NICs we are working with is supported only on the Mellanox cards, the NVIDIA cards, and we are thinking it could bring interesting results as it can, as I mentioned, decrease the loading and destroying latency of the rules, and it can potentially, what we have read from the documentation, support more rules than with the approach we are currently working with. The downsides of this API is that, at least as Mellanox says, it's not compatible with the API we are using currently, as the NIC doesn't allow both APIs used to be at the same time, meaning the drop filter as well as the bypass would need to be reworked completely in this new API. That would be everything from me. I thank you for paying attention, and if you have any questions, you can ask me now.
Hi. Did you consider using XDP instead?
I think SuriCata has support for XDP, but we are working with DPDK, and this is just present in the DPDK run mode. So it's more about experimenting and trying to this approach. And it's about working with the hardware, and potentially in the future with the NICs that have also handling of or support of the RT Flow API. So we are, at least my work is more directly with the intention of doing the RT Flow rules. So yes.
Yeah, so my question was quite similar. It was like, so I think Lucas Smith is your advisor, right?
Yes.
Yeah, okay. Smith. So my question was, yeah, what's the result comparison between this and his previous work? But like this, you just answer, so kind of answer like this.
All right, great research, Em. So I'm a DPDK user today, and one of the questions I have is with the new Suricata 8, like when would you recommend using DPDK versus the the new libsuricata stuff?
I think I'm not probably the right person to ask, as I'm working currently just not with the DPDK in general. I'm more specifying just on this hardware acceleration with RT-flow rules. I'm under the supervision of Lucas Smith. So, and I know he's working more with the DPDK in general in SuriCata. I think we can ask him, or we can. It would be better to contact, I think, him with the general stuff about DPDK and SuriCata.
Yep. Thanks, just the same. Great stuff.
Lucas, are you going to try to jump in? Or? Maybe I can ask my question in the meantime.
Yeah.
With the dynamic filter, there's sort of a race between the traffic and the setting of the filter. So SuriCata decides to set the filter. There's some latency before it becomes active, and maybe the flow is already done by the time it's ready. So I was wondering if you have looked at what that latency is and what the insertion rates are for the traffic.
This is a good. It's good. It's greatly represented in the articles I have mentioned. They are going deeply into insertion rates on the cards we are testing with, on the Mellanox cards. We didn't test the latency, as we will be trying with the RT flow, the template API, which should reduce the latency of loading. But we are considering this basically we are thinking if this is not the bottleneck for the results we have loading, and we still have like testing to be performed on this, but it's still a work to be worked on. We don't have like specific results as in SuriCata. How long does it take to create rules?
That's the XDP and DPDK question. I mean, bypass in XDP works, but it's only on the software level. What we were trying to leverage with DPDK is to push the bypass directly to the NIC itself, to the hardware, so the packets don't even go to over the PCI bus to the CPU and to the driver level XDP modules. XDP had a possibility to offload some of the subprograms to the hardware as well, but it was only supported on really, I think, only one NIC. I think it was called Metronome. Otherwise, all remaining NICs that support AF Packet Plus XDP program offloaded just on the driver level. So still the traffic goes to the kernel where it's basically filtered. If I could repeat the last question prior to Victor.
I remember who asked it.
I think the question was when to use SuriCata with DPDK or when to use the library mode, if I recall correctly.
Oh yeah. I guess that's a little bit hard. I think if you want to have SuriCata tightly integrated into your custom solution, then library to me definitely makes more sense. But the overall concepts are a little bit too far away for me. So whenever you want to do custom integration with Suricata, you always use the library, whereas DPDK is comparable with AF packet, AFXDP, and NFQ, and other full feature capture modes. And I think Victor, you asked about the insertion rates. Yeah, I don't think we measured that at this point. So, sorry, I can't answer that.
I think we have another question from the audience. Lukash, one moment.
Yeah,
At this point, it was more of a. Oh yeah.
Just one question. You mentioned about you mentioned about the asynchronous way of doing the config. Do you have any performance numbers by doing synchronous versus asynchronous? What's the improvement?
We don't have a specific numbers. We are just going by the NVIDIA specifications because it was developed by NVIDIA, 100 Mellanox cards, I think. And they have like documentation how this API work, and we are just going off that mention that it should reuse. We have yet not implemented it because it's like quite a different way how to handle the rules at all. Like it's differently loaded, differently destroyed. So we don't have like latent these numbers in Suricata, but yeah.
Is that part of your future work? Is that part of your future
implementation?
Yeah.
Yeah, it is. It is what I'm going to focus from now on. Also, we want to implement it and test it. See if the results are better.
Yeah, in DPDK world, it's always a little bit secretly specified. So sometimes you just need to implement it and see the constraints. The reason the asynchronous is the potential of Atom's future work is because, yeah, they promise much more rule capacity, especially in the Mellanox, in terms of millions of rules. And the asynchronous part should be similar as with the bypass thread that Atom implemented. It will be just native on the DPDK level itself. So yeah, we are probably just going to explore if it's feasible. To me, it seems so, and we just wanted to give it a try with this kind of work. We have one question on Zoom. So Joe Ransom asked, RT flow bypass will be applicable in IPS and IDS modes? If so, the bypass would the performance be? Sorry. If so, would the bypass, the performance be comparable to XDP bypass in IPS mode, where traffic is forwarded port to port if the target interface is on the same NIC? So far, Atom's work mainly targets IDS mode. IDS mode meaning it only drops the traffic. For kind of like IPS mode and forwarding from port to port on the same NIC, it's possible. But yeah, we are going one step at a time. So far, this has been Atom's main target. But it's possible also in RT flow as well.
Thank you for answering.
No problem.